The global economy is currently undergoing the greatest change since the Industrial Revolution. In order to remain internationally competitive, modern factories must be as flexible as possible and highly digitalized. The smart networking of people, machines and industrial processes is the ticket to a new age. Industry 4.0. In 1930, Henry Ford himself decided to build his next factory here. Today, the Ford plant in the Niehl district of northern Cologne is one of the largest car production facilities in Europe.
We have 134 assembly stations, but if only one assembly station stops, nothing will be built on the body shell afterwards. There will be no paint and no final assembly.
The plant is a city in itself, but everything runs together smoothly.
2 parts per minute, according to the daily working time, results in a total number of parts which currently make up 1,150 cars per day.
This hall is actually the size of 18 football fields. This shows how big we actually are here.
11 awards, 11 Engines of the Year awards. No automobile manufacturer has ever achieved this before.
The world is changing very fast. If we don't change now, in 6 months we won't be able to keep up.
Today, the factory is the only one for the Fiesta in Europe. Since 1979, around 9 million of these popular small cars have been produced here to be shipped all over the world. The journey from the raw material to the car begins at the goods receiving department in the pressing plant. This is where the steel is delivered from which the small cars are made. Employee Michael Wedel gets ready to unload the 30-ton steel coil. For this, heavy lifting equipment is used. In working slang of the plant, these rolls are called coils. Michael couldn't unload the coil by hand anyway. However, even in the further course of production, hardly any employees need to touch the individual parts, which turn into over 1,100 cars a day in the Ford plant in Cologne. No touch is the name of the concept to increase efficiency and quality. It starts with the receipt of goods.
About 1,000 quarter panels or 3,000 hoods are pressed out of it. On the computer, I take the call. That means that the interim storage is called by me whenever it's needed.
It is needed very quickly. The massive steel presses consume up to 5 kilometers of flat-rolled steel, or 10 coils per day. The gigantic pressing plant, which could comfortably accommodate several jumbo jets, leaves the visitor amazed. This is not only due to the enormous dimensions of around 200 by 250 meters, but also to the facts and figures. Press plant manager Klaus Pobans knows them all by heart.
In total, we have 11 pressing plant lines with a tonnage of between 400 and 3,600 tons.
The presses in the Cologne pressing plant supply Ford plants throughout Europe.
In total, 130,000 tons of steel are processed here every year. This is a huge amount, and it makes about 28 million parts. The 28 million parts are largely used in the Fiesta, which is produced here in Cologne. They also go to other plants such as Craiova in Romania, Valencia in Spain or Saarlouis.
Around 16,000 employees work at the Ford facility in Cologne, but only a few of them in the pressing plant.
We have a 3-shift scenario. That means we run 3 shifts a day, 15 shifts a week. We have 450 employees, not only from the pressing plant, but also from the logistics department. We've got a tool shop and a machine park as well.
The tools are the huge blocks that are used to press the steel into the various part shapes.
Here we're in press tool maintenance. We look after about 158 tool sets. Tool sounds small, but it's a little different here. The tool change time here is 15 minutes, which is actually considered quite good in European or worldwide operations. After that, robot programs are installed, new controls are installed for tool sets, the grippers are changed, and a test run's performed. A tryout is performed to see if the first parts are okay.
That the parts are processed efficiently with the well-being of the employees in mind is ensured by Sarah Gielen. The manager is convinced by the advantages of the no-touch concept.
This no-touch concept ensures that a part is automatically stacked in a standard rack. It can also be automatically entered or loaded and unloaded in our system in the body shop. This is a huge advantage in efficiency.
Anyone who produces as many steel parts as a car factory has to think about how best to move heavy parts from one plant to another, flexibly, fast and safely. One of the biggest challenges for the car manufacturer and the real strength of this mega factory lies in the smart design of its logistics. How that is put into practice in Cologne is demonstrated by production engineer Ibrahim Chifti.
Here is a packaging that we've specially developed for our patented process. The packaging is loaded with our camera and robot-based technology. This principle is patented and was developed by us. The patent is a gift to the company. It enables us to increase the quality and production efficiency in the factory. What's special about the packaging is that we normally have simple pallet cages where the parts are placed inside at random. With this packaging, the parts are placed inside in a particular order and available at any time in the factory and can be used optimally in the further processes. We've been able to introduce additional quality controls although the parts are dispatched to the packaging automatically. The efficiency has increased because we get more parts into this packaging, and the quality has also increased because the robots always put the parts into the packaging in the same constellation. This means there's no loss of quality during packaging or removal.
In the pressing plant, packaging refers to the transport systems that bring the parts from one place to another. Right next door, the packaging is prepared with laser assistance.
The laser up there shows green dots on the wheel, and according to the markings, the employee puts rods in or takes rods out again if there's too many. That was the first step we took to start this system. In the further course of the project, we're planning to build a system that relieves people of the hard work.
Optimization is carried out wherever possible at the Ford plant in Cologne. What is created here is often taken up by the entire group.
The no-touch concept, which we have put into operation here and developed ourselves, is now the basis for all plants worldwide. It has now been implemented because it's a huge benefit. However, we invented it here in Cologne. And of course, we now supply all the data to our colleagues within the Ford world, because it is important that we continue to work as efficiently as possible.
How the no-touch concept can be implemented successfully is shown in the next production stage. Uwe Weins is head of body shell manufacturing and is responsible for turning the parts supplied to him into car bodies. He's the master of more than 1,000 industrial robots, which also relieve people of the light parts.
We're standing at the beginning of the manufacturing process for the rear floor subassembly. Here we see a system that enables us to automatically grip bulk goods with robots, without the need for employees to pick up the parts, put them to one side, or transport them further. At this point, we choose a robot because the part is very well suited to being taken out of the box by a robot. This way, we relieve people of unergonomic, monotonous work, which is then taken over by the machine, and at the same time, we increase the overall efficiency when feeding the parts into the automation process. We use blue light to protect the camera from external light influences. Extraneous light would cause problems for the camera identifying the parts. This would lead to mistakes and losses in the production chain.
A body shell is highly automated. We have 1,200 robots in our body shop, and the creativity we have here in Cologne to invent things ourselves is high. We make sure that this can be done as efficiently as possible, and this experience is not only used in the body shop, but also in the pressing plant.
The pressing plant may use the experience gained in the body shop, but what is not used here is hidden beneath the surface.
Here you can see a whole range of monitors. On the monitors you can see what's going on in the basement. There are different conveyor belts because each press line contains a conveyor belt. All of the waste that is collected here goes up into a wagon. We have about 40,000 tons of scrap or offcuts a year, and that scrap goes back to the steel maker to produce new steel.
Beneath the hall is a hidden tunnel system in which conveyor belts run for kilometers.
You have to imagine that we have a total area of about 50,000 square meters above and below the pressing plant. Down here are all the hydraulics, all the scrap belts. In terms of the belts, we have a length of just under 2.5 kilometers located below the press line alone. They transport all the scrap to the wagons, which then go back to the steel producers.
This way, the waste parts might soon get a second chance to become a fender after all.
Since 2008, we've been using green electricity on the entire site, saving 160,000 tons of CO2 per year. We have special working groups which together always consider the costs because, of course, the world is changing and the techniques are new. We're also increasing automation, and every time we put our automation into operation, we think about where the electricity comes from and what we have to do here on site to keep our costs as low as possible.
Keeping costs as low as possible is the goal of almost all companies. Industrial companies therefore try to automate their processes as much as possible. This is where the AGVs helps.
AGVs means Automatic Guided Vehicle System, so no person needs to control the system. It works like this. We have two subgroups, right side and left side. In each subgroup, a part is produced, and the driverless transport system brings these parts from the subgroup to the main production line.
In everyday work life, the machines find their way around by themselves.
As I said, the vehicles drive fully automatically, and they also load fully automatically, but they only drive and load automatically if the current condition of our facility allows it. They have to finish one job first, and only then they can start the new one. Employees don't need to be afraid of the AGVs. They have all the safety features and scanners that recognize us as people and stop for us. At first, the employees were very skeptical. Depending on how often they were in contact with the vehicles, it took about 3 to 6 months for them to get used to the vehicle and its functions.
Just like the AGVs, body shop boss Uwe Weins continues to make his rounds.
Here we are at the so-called clamp belt, which is one of the core pieces in body shell manufacturing. And this is the first time we see the body shell actually taking shape.
The frame was equipped with an RFID chip shortly before.
Since the RFID on the vehicle carries all product information, the system knows which vehicle is to be built next by reading it out. 3-door or 5-door vehicle. The robots are then controlled accordingly and pick up the sidewalls. This means that the 3-door part is added to the 3-door floor, the 5-door part to the 5-door floor. The machine knows this completely automatically, and this process is carried out for the entire body shell construction. It's used in the paintwork and the final assembly as well, until the car arrives at the dealers, who then removes this tag during the first inspection.
Where chips set the pace and driverless transport systems whiz across the corridors, a so-called cobot is not far away. This refers to a robot that works with humans.
The special thing about what we see before us is the interaction between man and machine. The employee is protected by sensitive sensors built into the robot. And here, for the first time, we have the possibility for a robot to carry out its tasks unprotected, without a fence, and in a very confined space together with the employee.
His colleagues get along well with the robot.
His name is Uncle Manfred.
Uncle Manfred does the gluing.
I actually work with him. When I do my job, he does my prep work. And it fits. We meet right in the middle. That's a good thing. I don't get covered in glue, I'm clean, and that's worth a lot. No glue on my gloves, and that's a good thing.
However, Uncle Manfred is the exception. The vast majority of industrial robots are gruff powerhouses from which their human colleagues have to be protected by blue fences. Nobody should get in their way. Their rapid and monotonous movements do not take careless employees into account. Their fascinating moves are best observed from a safe distance. In the meantime, Uwe has reached the soldering section. Here, the roof and sidewalls are inseparably joined together. The lasers are so powerful that they are too dangerous for human eyes and must be concealed in a protective chamber. The automatic conveyor system conveys up to 50 car bodies per hour along the line to the soldering cabin, which resembles a garage.
We're standing at the end of the so-called laser soldering line. In this stage, we join the roof to the pre-welded body. The special thing about this is that we don't use spot-welded joints, but a laser soldering technique. This means that a laser supplies the energy and a soldering wire is fed in. This is how the connection between the roof and the sidewalls are made. In the cell, the roof is soldered to the sidewall. So, why laser? Laser technology is very precise and has a very high process speed. With laser soldering, thin, smooth seams are achieved, which you can see on the car afterwards. The complex part is that our devices have to generate a so-called zero gap. This means that the gap between the roof and the sidewall must be close to zero to within 1/10 of a millimeter. The big advantage of laser soldering is that the overall structure of the body can be kept much stiffer than with regular spot welding. This laser seam line is extremely sensitive to any deviation and must be joined with high precision. There's a camera incorporated in the laser head. It makes a high-speed recording of the laser soldering process. Our set parameters are at 3000 watts on a few square millimeters.
It's like concentrating the full energy of 50 domestic light bulbs on one point. The varnishing will show if they last. After soldering, the engine hoods and other moving parts are attached to the now fixed frame. The body can soon be varnished. At the end of the hall, where the pressing plant and body shell production are located, things become very calm and focused. Random samples are taken in the measuring laboratory to check whether the components meet exact specifications. Deviations are only accepted in the micrometer range. Engineer Georg Zieslik can rely on several systems for this: the futuristic-looking eagle-eye system and contact measurement.
We have different measuring methods here. One is optical measurement, and the other is tactile measurement. Optical measurement is contactless, i.e. the sensor doesn't touch the part. Tactile measurement has a measuring tip that moves up to the component and scans it in order to generate data that we have in the measuring machine's coordinates system. We have a measuring program for each component, which we then work through for a target actual comparison.
If the eagle eye or the tactile measuring instrument find deviations that exceed certain tolerances, the production process is examined. Even if it is faultlessly constructed, a car will not run without an engine. Conveniently, it's built right next door. Around 500 employees work in 3 shifts to produce the heart of the small car. Thomas Meyer is plant manager of the engine works, which is also located in Cologne. The engineer is proud of his product.
This engine is especially good because it's the latest generation. It's well tuned in terms of friction. It has bearing combinations coordinated in the micrometer range, which is hardly visible on your hand. It has an adjustable oil pump, which no engine in this class has. It has a split cooling circuit inside the engine. Regular in this class is 1. This one has 2.
What exactly happens inside the engine?
At the gas station, I fill up with petrol or diesel. In this case, it's petrol. The petrol is injected into a cylinder chamber via fuel pumps and injection pumps. This gets compressed and fresh air is brought in. Then there's a fuel-air mixture which is ignited by a spark. Then there's an explosion which causes the piston to move, the crankshaft to move, and the transmission to move the car.
The parts come either from other Ford plants or from suppliers, although not yet ready for installation. If the engine works, almost every part is worked at before it is installed. For example, each individual crankshaft must be precisely balanced. Meyer explains why.
These are balancing machines, and they're used to balance the weight of the crankshaft. The crankshaft is the heart of the engine and has to run smoothly at high or low revs. If the crankshaft doesn't run smoothly, vibrations build up and can lead to serious engine damage. A practical example. In the army, it's forbidden for many people to march in step over a bridge. The bridge can start to vibrate, and the vibration can destroy the bridge. In this case, it's the same. If there's an imbalance, a harmonic vibration builds up, and this can lead to serious engine damage. Therefore, you have to drill off certain weight proportions. This is then called balancing.
But how do the machines know how much material to drill off?
I know the drill diameter, the depth, and the density of the material, so we know how much we have to take out to have a defined imbalance.
The finely balanced crankshafts, the heart of the engine, are now ready for installation, but before the 2,000 individual parts become an engine, they pass through around 50 production steps. During this process, a data profile is created for each engine, which is used during production, but can also be useful afterwards.
Each engine gets its identification number at the beginning of the line, and a lot of data is collected for this identification number. If an engine should ever leak in the field, we can look at the engine number and find out when it was built, when it went through this plant, and when the sealant was applied.
However, sealing is not only important on the engine, but also on the body. The vehicle frames are now completely assembled, and the next step for them is the giant paint shop. Before they get their respective colour, the seams are thoroughly sealed. Production engineer Dennis Kuhn explains how.
The sheet metal parts are manufactured and welded together in the body shop. There are small gaps between the sheet metal parts, and we seal these gaps here. This is also known as seam sealing, and we do this here. We have 20 robots distributed over 2 lines. The body enters the line and is measured precisely by a camera system. This data is then transmitted to the robots. The robot is then able to place the sealing material exactly over these seams or over these gaps. Altogether, we build a total of 70 units per hour on both lines. After the automatic line, we have another employee area. The employees check the seams done by the robots, finish some of them, and then lay additional seams, especially in areas which are difficult to get to, like in the door areas.
Before the seams were sealed, the frames were only given a primer coat. This area is the last production step in which they are not yet assigned a specific order. Dennis has arrived at the paint line where the bodies get their paint, an area that is strictly separated from the rest of the paint shop, as the whole production section is called. Only now, on the paint line, are the car bodies given an identity. Before the paint is applied to the primer, a very soft and flexible cleaner does its work. The so-called EMU rolls are supposed to remove the very last particles of dust.
The name comes from the fact that the system is equipped with feathers from the EMU. They have the property that they absorb dust very well. That's why these side rollers run over the surface of the car body and bind any layers of dust.
Apart from the EMU feathers, the system is highly computerized.
First, we apply the finishing coat in the paint line with 35 robots. This is the visible coat that gives the Fiesta its coloring. We're able to apply up to 16 colors at the same time in this paint line. We have an intelligent car body control system, which specifies the colors as the bodies enter the paint line, depending on the subsequent clear coat which is then applied. The whole thing starts in the primer because the colors build on each other. First comes the primer, which is the basic layer, and depending on the primer, the top and the clear coat is applied. A darker primer is usually applied first with a darker coat on top.
The 2 employees can breathe in without concern despite the nearby paint spraying facilities. Due to strong ventilation in the paint line, it is neutral in smell.
Basically, we suck in fresh air from the outside, which is conditioned and also humidified. This air is then passed through filters in the ceiling and directed from above down into the paint line. This is known as controlling the airflow velocity, and it also helps us to ensure that excess paint particles that do not land on the car body are deflected and discharged.
In Thomas Meyer's workshop, the engines are now fully assembled and ready for the black light test. That is, the examination with black light. Will they find a leak?
I have a camera, I have black light, and there's oil in the engine. The engine has already been tested cold, has been rotated a few times, and then I'll have a look if there's oil leaking from the engine. The oil contains a fluorescent agent, which can be seen with the black light. On the screen, there are predefined areas of the engine where there could be leaks, component pairings that have been sealed, and where oil can leak out. The peculiarity of our engine production is that we test 100% of all engines using this test. This test ensures that the engine doesn't leak, and only 2.5% of our engines are tested using the hot test. That means 2.5% of our engines are started. The rest is only tested cold and then installed in the vehicles. This is a special feature for the high quality standard we have here. We do not have to test 100%.
Quality inspector Thomas Biller is responsible for the samples taken from production. He carries out the hot test or the hot run, and that too begins in the dark. Every engine that is fired is again thoroughly checked for possible leaks using a UV lamp. If Thomas doesn't find anything, the hot run can begin.
This is a function test bench for the engines coming off the line. Random engines are tested here. Other car manufacturers are still at 100%. We started at 5%, we're at 2.5% now, and for quality reasons, we always do spot checks. For us, it's absolutely legitimate to have 2.5%.
Thomas makes final preparations. The test engine is connected.
Here, the engine is fired with petrol, filled with water and connected to the electrical system. That's a hot run.
A lot of experience is needed for the job. There are various things Thomas has to pay attention to.
I'm examining the engine to see if there are any faults. For example, is there a leak during the test run? Does the engine make any noises, any rattling, or does it function faultlessly?
He detects suspicious noises using an unexpected method.
We have a very old method for this, the so-called ear trumpet. When I put it on the engine, I hear different noises. You have to be trained for this. You have to have some experience in the automotive field because the engine makes lots of different sounds. Every part sounds different, so you need experience to hear it.
As soon as everything is ready, he starts the test routine, about 15 times per shift. Checks are also carried out in the paint shop.
First, the car bodies pass through a dirt and paint detection machine. The machine that you can see behind me spots dirt in the finish. A light portal is moved through a frame and cameras spot anything caught in the painted surface. The lamps and the camera system, together with a sophisticated algorithm, detect these inclusions and show the faults on monitors. The employee will then rework the defects while the process is running.
Here, every flaw in the paintwork is discovered nowadays, however, mainly by cameras.
In the past, the employees had to find the errors themselves. This has now been made easier for them with this system. This means they can spend more time processing the faults and less time looking for and finding them. Nevertheless, the employee still has to keep a close eye on the entire surface. The system itself stores the errors associated with the car body and outputs them line-tracked with the car body on the conveyor belt. This information is also recorded and then always displayed at the exact workstation where the monitors are located.
And it almost always works.
Now it's on the next one already, the next car.
Under the light, which clearly highlights anything that's uneven, the cameras on the ceiling detect spots that are only a few millimeters in size.
We have a tolerance. Blue are small faults up to 0.3. Anything above that, the larger faults, is then marked in red.
Spotlessly polished, the bodies leave the paint shop and disappear into a huge silo. Here they wait to be picked up for final assembly. A fully automated system takes care of the storage and pickup, always taking exactly the car body that is next in line, depending on the order and delivery time. Betty Chirian Otto is one of two people who coordinate the final assembly at the Ford plant in Cologne.
We are responsible for safety at work, for the quality of our Ford Fiesta and, of course, for the number of units we have to produce here every day. By this I mean that we produce an unbelievable 1,150 vehicles per day via two parallel systems with a cycle time of 82 seconds. This means that we have two Fiestas coming off the assembly line here every 82 seconds.
To be able to handle these quantities systematically, Betty and her team need one thing above all else: space.
This hall is 18 football fields in size, and this really shows how big we are. About 326 employees per shift work on our Ford Fiesta, which has an incredible 4,300 parts. How do we, as division managers, actually keep track of things here? We are indeed dependent on our great employees. In addition, communication is incredibly important in this large area. How do we do that? We communicate here exclusively on mobile phones. Given the fact that we produce two Fiestas in 82 seconds, we have to act very quickly here. So in 82 seconds, we can't afford a 60-second break, as that might mean we've already lost one Fiesta like this.
Anyone who doesn't know their way around here can easily lose their bearings, but everything is strictly organized.
We have 10 lines here, each with a foreman. A foreman has about 30 to 40 employees. A line is basically divided into 4 teams, which are supervised by a team coach who always has to step in when an employee needs to go to the toilet, or when a quality problem arises, or when there's a problem with a tool. So it is possible to act flexibly and provide support.
The employees also get support from a computer, more precisely from a touch screen on which they can complete a virtual training session directly at their workplace. All the stations in the final assembly and all the required actions follow a set logic. This is clearly explained in short 3D tutorials.
Hier ist ein virtuelles Training. Hier siehst du im Video jeden einzelnen Arbeitsschritt, den du durchführen musst.
Next week I'm supposed to learn a new job. Before that I was shown virtually which movements I have to do there. If I want to learn a new job and develop my skills further, I ask the foreman if that's okay. If he gives me the okay, we train this virtually first and then at the workplace. And in an emergency, it can also happen that I have to step in. Every employee can go to the touchscreen to acquire the knowledge they need. It can also serve as a refresher. If we're short-handed, this might happen once a month, otherwise according to demand. If I feel ready to go on to another workplace, I can take the virtual training and learn about it. Employees already know their own work steps, but we need them to be flexible. There has to be some rotation among themselves so they can also swap jobs from time to time. Some members of our team would like to rotate after every cycle. There are others who have reached a certain age and are only doing one station and are happy with it. We react to what the employees themselves would like.
Only a few steps remain until the 4,300 individual parts have become a roadworthy automobile. A great moment. Chassis and body are united. In Cologne, however, there is an additional special feature.
We're here at the marriage. The marriage is the joining together of the chassis and bodywork. Basically, this is where the heart is put into our Fiesta, and this is what every car manufacturer calls it. The special thing about our marriage, in contrast to all our competitors, is that our marriage is fully automated. No employee has to take responsibility for the precision of this combination between body and chassis.
The automation continues to the end. Now the front, back and rear windows are fitted to the small car. The different possible configurations are managed by the systems independently.
Representative for all our systems, these line here use so-called scanners which scan the label on the roof of our car bodies. Basically, they pass the information onto our systems, which then know exactly what type of vehicle it is. They know exactly what to do, which type of glass to pick up, whether light or dark, with chrome or without chrome. And especially with regard to our 3-door or 5-door models, it is relevant to know how many windows are to be installed in the bodywork.
Equipped with the right set of windows and married to the chassis, the car is now fitted with the wheels. Then it's completed. Since the coil was delivered to the press shop, it has taken 12 hours to get the Ford standing on its own axles for the first time. But finished? Not quite.
In the very last step of our entire production, so-called ECATS devices are placed on the steering wheels and connected to the vehicles. These devices are used to configure or program functions within the vehicle. These are things like the radio settings, for example, or the radio itself. The touchscreen inside the car must be configured and programmed according to customer requirements and wishes. This includes the interior lighting, which goes on or off in certain modes. All this is configured and programmed using these ECATS devices. However, there is also one thing that is indispensable in final assembly. An employee has to physically perform various actions. He has to operate the clutch, the brake, or switch the lights on and off. The device as such cannot do this.
Now the Fiesta can literally roll off the proverbial assembly line as one of 1,150 in Cologne every day. Round the next corner, the customers, or rather their critical eye, is already waiting.
We are here at the final inspection, the CAL, or Customer Acceptance Line as it's called. We look at the car from a customer's perspective. In each shift, we look at about 600 cars. We inspect the entire outer skin of the vehicle, move around the vehicle to check for faults, dirt inclusions, dents and bumps. The second step is the interior inspection, where the doors are opened and all interior panels are checked. I'm always happy when we check a car and it's turned out well, because then the customer's happy. And we all benefit from it. That's why I drive a Fiesta myself.
In 1932, the first vehicle rolled off the production line in Niehl. At that time, the capacity was still 60 cars per day. Since then, the output in the Cologne mega plant has increased 20-fold.